Checking if the validation V is the same for any combination should be as simple as saying that for P1, implying P2 and P1, implying P1, we run this by saying our total number of combinations on this are these ones, so 0, 0, 0, 1, 1, 0, and 1, 1. So we get 0, 0, 0, 1, 1, 0, finally 1, 1. And so the validation, okay, actually, you know what, straight out of the box, no, never mind. Yeah, we should do the parentheses first. Okay, so 0, 0. 0 implies, so by default it's 1, so the result would be 1. 0 implies 1, the default would be 1. 1 implies 0, the result will be 0, and thus there is one case in which we will get a 0 here. Okay, so for the sake of checking if the validation is 1, we will assume that in the worst case scenario we get a 0 here. For in here, so for P1 we can have a 0 or a 1, and if 0 implies 0, then we get a 1, and if 1 implies 0, then we get a 0, and we assume the worst case scenario in which the outcome can become a 0. And so we prove that, so this can be 0, and yeah, and this can be 0, and therefore we've made a mistake. I've made a mistake because I evaluated this part independently of this part. Why is that a mistake? Well, because P1 is referenced twice, and so whichever value P1 takes, this one other will have to comply. So all we really had to do is, well, all the extra we had to do is check, well, we had this, right? The truth table, 1, 0, and 1, 1. And so this combination, we found out that it resulted in 1. Now, and here we had the possibility for 0 and 1. And so we say that in case, down here, in case the P2 is 1 and P1 is 0, sorry, that is not a 1, that is a 0. That is a 0. This is very finicky, yeah. Okay, in this case the output will be 0. However, the funny thing is that P1 in this side at the same time must have the same value assigned, so this one is not even considered in such an occasion, and we've covered all of the others. So for any other occasion, this will be the result will be 1. For this in particular, the result will be 0. Now, if we use this output, we must remember so this is the only scenario in which it can be 0, and this is the only scenario in which no yeah because alright, so this is quite tricky actually. This is quite tricky. I'll try to do this in a different way. This one obviously is not working correctly. So again, let's go with the truth table. So 0 and 1, and 0, 0, 0, 1, 1, 0, 1, 1. And let's regard these as, so the cases in which we have 1 are directly connected to this, and the cases in which we have 0 are directly tied to these cases. So in other words, we could strategize like such. And for this, we can say that we have these matching sets. Which we can pull down here and restructure in the following way. 0 for P1, implying P2, which implies P1. We can use the squares first, so 0, 0, and then 0, 1, 0, followed by the circles, or non-perpendicular shapes, and we get a 1 from here, and a 0 and a 1, and then this one right here, which is 1, 1, 1. Okay, so we've reordered the truth table because we want to fashion out any possibility of the output being equal to 0. If that is the case, then this is not a equal validation case. So let's say if we have this scenario in which this will always be 1, this will always be 1, so this is 1, this will be 0, but given that 0 will then negate anything that happens here, the result will be 1. Now, in here, the result will be 1, and then we take out the big combo, and the result will be 1 once again. So we'll have 1, and 1. 1 implies 1. And finally, 1 implies 1 implies 1 will be 1. So in every single case, in every possibility, we have 1. Thus, we have confirmed the equivalent, the equivaloration.